Hello and welcome to lab number 6. The title of this lab is Total Internal Reflection. Total internal reflection represents an important property of light that's at the core of operation of optical fiber cables. Optical fiber cables have found many applications these days. They are providing for almost unlimited bandwidth and supporting all these huge data transfers that we are witnesses of. So it's very important to understand this important physical property of light called total internal reflection. Total internal reflection represents a special case of a refraction of light. There are two important conditions that must be fulfilled in order for the total internal reflection to take place. The first condition is that the light is attempting to pass from optically more dense into optically less dense material. And number two, the angle of incidence in such a case must be larger than so-called critical angle. So the goal of this lab is to observe the total internal reflection in acrylic rod. So we are going to use acrylic rod, which is our expanded imitation of the optical fiber. So we are going to demonstrate the total internal reflection effect in the acrylic rod. We are going to set up the experiment, measure angles and record relevant data, and then we are going to use the experiment data and Snell's law to calculate the critical angle. And finally, you're going to give some thought about the applications of the total internal reflection in addition to the most important application, which is optical fibers. In this lab, we are going to use a laser pointer as a light source, an acrylic rod to observe the effect of the total internal reflection, and then we are also going to use the protractor to measure the angles. We also are going to need the pencil and a large white sheet of paper. To observe the effect of total internal reflection, we are going to use this short piece of acrylic rod. So this is going to be an expanded imitation of optical fiber. Optical fiber, the diameter of the core of the optical fiber is 10 to 60 micrometers. This acrylic rod, obviously, it's about ½ inch. So the diameter of the acrylic rod is significantly larger. That's going to enable us to shoot the light into the acrylic rod and observe the phenomenon of total internal reflection. To observe the total internal reflection, we have taped down our acrylic rod onto the white sheet of paper, and we also positioned our laser pointer at a specific angle, and then also taped it down to hold it steady at a place. And what we can see here is that total internal reflection is actually taking place. And the reason why I'm making this statement is because we are seeing a lot of light over on the other side coming out of our acrylic rod. So for the total internal reflection to take place, there's two conditions that need to be fulfilled. The total internal reflection is a special case of the refraction of light. We know that light propagates along the straight lines if it's moving through the same medium, and when it is passing from one medium into the other, the light is going to bend. So in this case here, what we have is acrylic, which is one of the materials, and then we also have the surrounding air. If the light is moving from optically more dense into optically less dense material, the light is going to bend away from the axis, and that's the first condition to be fulfilled for the total internal reflection to take place. So the light has to move from the optically more dense into optically less dense material. So here we have a light that entered the acrylic, it's propagating through the acrylic, and then it is going to hit the outer edge of the acrylic, and it's going to try to pass from the acrylic into the air, which is passing from the optically more dense into the optically less dense material. So that first out of two conditions for the total internal reflection is fulfilled. The second condition for the total internal reflection is that the light is hitting the surface between the acrylic and air at an incident angle that's larger than the so-called critical angle. We are going to calculate the critical angle in this lab, and in this specific case that you're seeing right now in this video, the laser has been so adjusted to provide for the incident angle larger than the critical angle, and that's why we are observing the total internal reflection at this point, meaning the light is bouncing back and forth through the acrylic and coming over on the other side, and you can see a lot of light. Now it's important to clarify two things here, not to get confused what the critical angle is. What we see here is the front surface of the acrylic rod, and we have the laser pointer. So laser pointer is going to produce the laser beam. That laser beam is going to go through this short path here that's in the air. It's going to hit this front surface. It's going to bend at the front surface. There we are moving from the optically less dense into the optically more dense material. And then the light is going to bend in the acrylic. So it's not going to continue along the same path as it is the path of the incident beam. So it is going to enter the acrylic, it's going to bend at a specific angle. So we are going to have the light moving through the acrylic rod that's been already refracted at the front surface. And that light that already entered the acrylic rod is to be considered the incident light ray, for which we are going to calculate the incident angle that needs to be larger than the critical angle. So don't confuse the launch angle here in the air with incident angle or critical angle that's inside the acrylic rod. So the whole effect of the total internal reflection is not happening at this front surface of the acrylic rod. It's happening after the light entered the acrylic rod and when it attempts to leave the acrylic rod and leaks back into the air. So in order to show the effect of the total internal reflection more clearly, we are going to dim the light in the room and continue with the lab. Now that the light is dimmed in the room, we can observe the total internal reflection in a much more clear way. So you can see here that the light exits the laser pointer, moves along this short stretch in the air, and then enters at the front surface, enters the acrylic rod, and you can see this path here of the light to the acrylic rod. That's going to be considered our incident light ray, for which we are going to calculate the incident angle, and that angle has to be larger than the critical angle. And then you can see here, as the light attempts to exit the acrylic rod, the total internal reflection takes place. So the light is not exiting the light rod, but it's totally internally reflecting along this beam here that can very clearly be seen. There are multiple effects of the total internal reflection where the light keeps bouncing back and forth in the acrylic rod and finally exits over on the other side. So you can see a significant amount of light over on the other side because light has been totally internally reflected multiple times along this acrylic rod and then finally exits over on the other side. So if you take this laser pointer and you start changing the direction at which you are launching the light into the laser pointer, meaning you're changing the angle at which you're shooting the light into the acrylic rod, you can observe both the case of total internal reflection, as is the case here, and then also at certain angles you may observe that total internal reflection does not take place. In other words, the light is going to be leaking out into the air and you won't see that much of a light over on the other side. Okay, so to calculate the critical angle, we are going to trace the beam coming out of the laser, which is going to be this one here. We're going to also make a few dots and make a footprint of the acrylic rod, and then we're going to do necessary calculations. So what I'm going to do here is, as you can see, we can log the beam and see where is the front surface of our acrylic rod. So we're going to make the footprint of the acrylic rod. We are also going to mark the point at which the first total internal reflection takes place. And finally where the light enters into the acrylic rod. Now that we marked all the points that are important to us, we are going to remove the acrylic rod and the laser pointer and improve our sketch and then do necessary measurements of the angles and the calculations. Let's now improve our sketch. So what we can see here is a footprint of a laser here. We have a footprint of the acrylic rod, and then we have a few dots here that indicate the path of the laser beam. So let's improve the footprint. First the laser. So here's our improved sketch. So we can see here laser and an acrylic rod. We can see that laser is shooting the beam at an angle, and then here at this front surface, the light that's exiting the laser and passing through the air is going to hit the acrylic rod, and then it is going to enter into the acrylic rod. At this point that we labeled as a point A, the first refraction is taking place, where, as you can observe, the light is bending. It's not continuing along the same line as in the air, but it's bending into the acrylic. And then here we have light that's propagating to the acrylic, and it is going to hit this surface here between the acrylic and the air, since we have acrylic being optically more dense than the air being optically less dense. At this point here we also satisfy the condition of the incident angle being a more than critical angle. That's why at this point here, that's labeled as point B, we have a total internal reflection. The light bounces back into the acrylic, so it's not passing, it's not leaking into the air, but it's bouncing back into the acrylic, continues along this path here, and then here again it's gonna hit the surface between the acrylic and air and total internally reflected, and it's gonna continue bouncing back and forth in the acrylic. So for us to calculate the critical angle and see whether our incident angle is larger than the critical angle and confirm that it is, we have to calculate the index of refraction of the acrylic, because that's going to be the variable that we need for the calculation of the critical angle. The way how we are going to do that is we are going to focus on point A first. So in this point A, we are going to use the effect of refraction to measure the incident angle and refracted angle, and then calculate the index of refraction of the acrylic, and then use that information about the index of refraction of acrylic to move over to the point B at which we are going to calculate the critical angle. So we are focusing at point A and the effect of refraction that's taking place there. I have created an axis that's perpendicular to the front surface of the rod at the point A, and extended our incident light ray beyond the laser, and then also this refracted light ray here I also extended further into the air. Obviously light does not enter the air, so this is just for the purpose of measuring the angles that we are going to measure right now. So the first angle that we want to measure is this angle here. So that is going to be our incident angle. So we are going to use the protractor to do that. So the angle that we are measuring is 10, 20, 30, 40, about 44 degrees. So our incident angle is going to be equal to 44 degrees. And then we're going to go over on the other side. Our refracted angle is this angle here. So the angle that refracted light ray that entered the acrylic makes with our axis that's perpendicular to the front surface. So this is our theta refracted. So let's measure that angle. So I'm measuring 10, 20, about 23 degrees. So our refracted angle is 23 degrees. Now we are going to use the Snell's law of refraction. So we can plug in 1 for the index of refraction of air times sine of 44 degrees equal to unknown index of refraction of acrylic times sine of 23 degrees. Let's calculate sine of 44 degrees is 0.69, and then sine of 23 degrees is 0.39. So from here we can calculate the index of refraction of acrylic to be equal to 0.69 over 0.39, or equal to want 1.7677. So to calculate the critical angle, we have this formula. So theta critical is equal to the inverse sine of n air over n acrylic. Let's substitute for these two indices of refraction. So for air we have 1, and for the acrylic we have 1.77. Also important to mention that your index of refraction that you calculated for the acrylic may be different than mine based on the way how you measure these angles, and of course based on the certain variations in material properties that these acrylic rods are made out of. So after we substituted for index of refraction of air and index of refraction of acrylic, we can continue our calculation here. So let's do the fraction first. 1 over 1.77 is equal to 0.565. And then finally we can take inverse of sine for this number, and we get 34 degrees. So our critical angle is equal to 34.4 degrees. Now that we calculated the critical angle and we came up with the value for the critical angle of 34.4 degrees, we want to check our point B, where we are claiming that we observe the effect of the total internal reflection. We want to see whether at that point our incident angle was larger than the critical angle, because that's one of the conditions that must be fulfilled in order for the total internal reflection to take place. So again, there's two conditions that need to be met. The first condition is that the index of refraction of the medium that light is coming from has to be larger than the index of refraction of the medium that the light is attempting to enter. So in this case here at the point B, we have the light that's coming from the acrylic, and at this point B the light is attempting to go into the air. So we are going from optically more dense into optically less dense medium. So the first condition of the total internal refraction is fulfilled. Second condition is whether this incident angle, so that incident angle that we're talking about, so now we are considering this light here that is in the acrylic. So you can see this path here. That's now considered our incident light on the point B. So I have extended this beam here, this path, further back. And then also at point B, I created the axis that's perpendicular to the edge surface where the total internal reflection is taking place. So that's this axis here. So the angle that we want to measure is this angle that the incident, this incident light ray here makes with the axis. So that's the angle that we want to measure. So I'm going to sketch it here. So we're talking about this angle. We want to make sure that this angle here, we're going to call it theta 1. Want to make sure that that angle is larger than the critical angle, because that would be the second condition for the total internal reflection to take place at point B. So let's measure that angle. So we are going to position our protractor along the axis, and we are going all the way to right here. So we're measuring 10, 20, 30, 40, 50, 67 degrees. So our theta 1 is equal to 67 degrees. So what we can observe is that our incident angle at point B is larger than the critical angle, which means that the condition for the total internal reflection is fulfilled, and that's why we observed the total internal reflection at that point and confirmed it to calculations.